How could we let the aliens know that we're here? What would a lunar eclipse look like from the surface of the moon? And could we see a supernova in real time? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I will gather them up and I will answer them here. Just to let you know, I'm going to be traveling for the next couple of weeks, so I'm not sure if I'm going to be able to record the Question Show. I'll try, but it might be you have to wait a couple of weeks before we get the next one. All right, let's get into the questions. HPA 97. Could we effectively make ourselves more visible towards other intelligent life out there by placing green glass or something that only allows green light to pass through around the sun so that we would stand out with a green star? You've probably heard that there are no green stars. There are blue stars, there are red stars, there's orange stars, yellow stars, but there are no green stars. And that's weird because the sun is giving off the majority of its photons. Sort of if you look at like a curve of all the different kinds of photons that the sun gives off, it gives off a lot of green photons, and yet the sun doesn't look green. And that's sort of just due to all of the colors coming together. It looks white from our perspective when you add up all those colors, and there are no green stars out there. And so HPA's idea is like, could we just put a filter, some kind of gel in front of the sun that would then make it look green, and that would just be obvious to the aliens that we are here? And yes, if you were to put a giant shell of green around the entire sun, then it would send out a very bizarre signal to other intelligent civilizations out there that there is a very bizarre thing going on with this star. If we saw a green star out in the universe, it would be the cause of an enormous amount of curiosity by astronomers. But like, that sounds hard. Like, it sounds really difficult to enclose our sun. Because remember, you got to think about all of the different angles that the aliens could be watching us from. And so it's an enormous amount of an engineering expense to surround the sun just so that we can, say, hey, we're here. Now, there are some ways that you can do the same thing, but with vastly less effort. In fact, things that are starting to approach what we could do soon. So instead, you just need to give the sun a satellite that is a funny shape. So you will expect that all objects that are orbiting around the sun or any star are going to be spherical, the big ones. And that's because hydrostatic equilibrium wants to pull together the mass of anything from a giant planet to a dwarf planet into a sphere. And so if you made a triangle, like maybe you made it out of some kind of solar sail material, and you had this triangle orbiting around the sun, then anyone who's using the transit method, like how we're finding exoplanets, they would look at the star and they'd see this really bizarre light curve. So a normal light curve goes like this, and then it goes down when this planet is blocking the sun, and it comes back up and goes over. And that is because a round object is passing in front of the sun. But if you had a triangle, it would give a very different light curve, one that would be just immediately obvious. And so astronomers here, if they saw a weird light curve, they'd be like, what is this? We don't know what this is. It appears to be the shape of a triangle. How can planets be triangles? There must be some kind of intelligent civilization there. And so really, you just need a giant triangle made of some gossamer thin solar sail material that is orbiting around the sun. But you still have this problem of it not being in all directions for all people. So you're going to need multiple of these satellites that are orbiting around the sun at different angles so that eventually you can cross off as much of your nosy neighbors as possible. But to kind of go back to your original idea, if you did enclose the sun in not necessarily a rigid glass ball, which would be very complicated, it would be unstable and it would drift one side and the sun would melt through the thing, you could just surround the entire sun in satellites that are collecting solar power and using it for some purpose. And eventually you're going to block enough of the light from the sun that the sun will no longer be bright in the visible wavelengths. It'll be visible in infrared. And an infrared star would be very weird too. And if we saw a star that was sort of putting out the energy of the sun, but it was mostly in the infrared, the heat that is being emitted from these satellites, then that would be a very unusual thing and require a follow-up study. And that is a Dyson sphere. And so, you know, when you think about the search for intelligent civilizations, part of this process is to think, what would we do? What could we do if we wanted to send a message out to the universe that we're here? What's on the table? What are some of the possibilities that we can use? And so, you know, the direction you're going is one, there's a bunch of others. We could put certain chemicals into the atmosphere of the Earth. Oh, we already did that. Well, they're going to give a sign that some, you know, industrial civilization is here on planet Earth. Or we can see things that we're doing to our environment that are putting it out of balance. That could be detectable. Our technology, our satellites. So there's a lot of stuff that we're doing to give a signal to the universe that in theory, you know, we can search for other civilizations doing the same thing. And if you wanted to be intentional about it, that would all just sort of take it to the next level. You probably noticed the Star Trek planet name that appeared above my shoulder. This is a way for you to vote, for you to tell us what you thought was the best question of the week. And the winning question this week was Betazed, Christopher Jacobson. How will Japan keep the astronauts from bringing dust into their Artemis pressurized rover? So thank you everybody who voted last week. Great question, great conversation. Very good news that Artemis is going to get a rover from the Japanese. So we're going to list a different planet name for each question and throughout the entire episode. And then at the end, you can just write down the question in the YouTube comments down below that you thought was the best one. And then I will gather those up and we will celebrate next week. Don't forget to vote. Alex, just Alex. Can somebody from the team please review my question from the last episode about the solar lunar eclipse? I meant something else and added a more elaborate comment. Some people understood it and take it as I meant it. Take two, please. All right, Alex. So the question that you asked was, what would a solar eclipse look like from the moon? And this was a couple of weeks ago, and that was the question that I answered. And I suspected you were asking, what would a total lunar eclipse look like from the moon? But because we had just had the solar eclipse, because we got these really cool images of the solar eclipse happening, that was the answer that I gave. I don't know, is it like wishing on the monkey's paw that you get the question that you asked? The turkey is a little dry, but sure, round two. Let's answer the other question, the one that you intended to ask, and tons of people in the comments were like, I don't think that's the question you wanted to ask. I agree. Let's answer the question that you wanted to ask, which is, what would a total lunar eclipse look like from the surface of the moon? And so from our perspective, a total lunar eclipse, this is when the moon passes into the Earth's shadow. And then the light from the sun is blocked on the moon, and you get some really interesting phases of this process. And they only happen during a full moon. And in fact, they are really nicely aligned with total solar eclipses because, you know, when you think about the geometry, you've got the sun, you've got the Earth, you've got the moon, and the moon is on an inclined orbit from the plane of the ecliptic, where the Earth is located. And so sometimes the moon is a little higher than the Earth in orbit. Other times the moon is a little lower, but sometimes the moon and the Earth and the sun perfectly line up. And typically you get these periods where you'll get like solar eclipse, lunar eclipse, solar eclipse, or partial solar eclipse, lunar eclipse, partial solar eclipse. And so you get these combos of multiple. So often if you hear that there's a lunar eclipse, you can expect it's going to be a solar eclipse very soon after. And so when this happens, right, the moon is passing into the Earth's shadow. And from our perspective, let's see what we see. It takes about 3 or 4 hours. And in the beginning, we see just this really slight shadow on one limb of the moon. And then after a while, we get this chomp taken out of the moon that gets bigger and bigger and bigger. And the moon is bright, full moon white. And then you get the very dark chomp that's taken out of the moon. And then at totality, when the moon has fully passed into the Earth's shadow, the whole thing turns red. And it's quite amazing. I really like lunar eclipses, and you know, they're great because they're visible from an entire hemisphere. Anyone can watch them. They're completely safe. You don't have to travel. You just wait a couple of years and you're going to get to see a lunar eclipse. And then the red goes away, the chomps start to appear on the other side, and eventually the moon passes out of the Earth's shadow and it is completely in sunlight again. And so if you were standing on the moon, what would you see? You would first see the sun get closer and closer and closer, or the Earth getting closer and closer to the sun in the sky. And then you would see the Earth actually start to pass in front of the moon from your perspective. And then you would see the Earth completely in front of the sun from your perspective. And then at that moment of totality, you would be seeing the sunrises and sunsets of the entire Earth ringed around the planet. You're seeing the light passing just through the atmosphere of the Earth, and it would cast everything around you in this red color. And then it would reverse. You would see the sun appear from the other side of the Earth, and then the sun would be back. But the sun from the moon's perspective, or the Earth from the moon's perspective, is much bigger than the sun. So it's not like the way the moon and the sun are from the surface of the Earth, where they're roughly the same size. And so you would see this process happen. It'd take a long time for the sun to disappear and go completely behind the Earth. But that time when you would see the Earth ringed in this red glow would be really amazing. So that alone would be worth going to the moon to watch a lunar eclipse. I hope that answers your question, unless there's like a third version of this that I don't understand. Wax paper. Will it ever be possible to record a supernova materializing in the sky in real time, actual video instead of before and after images? I don't know if you're ever going to get video of a supernova going off in real time, but you're going to get a series of images that are going to be taken as quickly as possible, which can then be stitched together to make a movie. So I think that's close enough. Now, why have we never seen a video of a supernova going off? That's because they happen really far away, millions of light years away in various galaxies, and they happen at a completely random basis. So once every couple of years, you can expect to see a supernova going off nearby to us, like within tens of millions of light years. And then you see them more commonly farther and farther away, where you can't even sometimes even see the galaxy. You can just see this bright supernova going off. And so there's too many galaxies to look at all of the time to catch the moment that the supernova goes off. The one we want to see is the one that goes off here in the Milky Way, relatively close to us. Like safe enough that we're not going to take any damage, but close enough that we can see the star, we can watch the star die, and we can see what happens after the fact. There have been several examples of this happening in human history. We've got the one that was seen by Tycho Brahe, I think in the 1600s. We've got the Crab Nebula, which happened in 1054. So there's been, every few hundred years, a supernova goes off that's relatively close by. And so once again, though, there are 100 billion stars in the Milky Way. So how can you get an advance notice of a supernova going off? Neutrinos. Now, I know this sounds really weird, right? Because light is going at the speed of light and neutrinos go slower than the speed of light. And yet, when a supernova goes off, we will see the neutrinos first and then the light coming from the supernova. And you're asking, why? How's this possible? And what happens is that when you think about light trying to escape from inside, say, the sun, it can't just be generated as gamma radiation at the core of the sun and then just blast out of the sun. It has to do what's called a random walk. The gamma ray is emitted, and then it can only get a tiny distance before it gets absorbed by another bit of the core of the sun, and then it gets emitted again, absorbed, emitted, absorbed, and does this random walk out of the core, through the radiative zone in the sun, and finally gets into the convective zone and is able to follow these kind of lava lamp blobs up to the surface of the sun, and then it can escape off into space. And it's thought that it can take tens of thousands, maybe 100,000 years from a photon that is generated inside the sun to actually get out of the sun. And so when you have a supernova, you kind of have the same thing, which is that the star dies, it implodes, all of this material is falling down inward, and you get this explosion, all of this, this giant thermonuclear explosion that goes off at the heart of this supernova. All this energy is built up. It's going to be released. It's going to make it out, but all this infalling material is blocking it from being able to make it out into space. But this process generates neutrinos, and neutrinos go through anything. They can go through lead, they can go through stars. And so the neutrinos immediately escape from the star as it's exploding, fly off into space, and then the light arrives minutes or hours after the neutrinos. And so this is an opportunity. And so astronomers have actually built a supernova alert network where they're able to watch the sky in all directions in a relatively close distance, like a few hundred light years away, maybe a couple of thousand light years at the most, and be able to detect this distinct flash of neutrinos coming from a relatively nearby supernova in time to be able to then alert the rest of the astronomers with all of the different wavelength telescopes, point them at this star, and wait and watch the explosion going off. And right now, we're in the initial stages of what these, the distances that these supernova networks can do. The Chinese are working on a new network that's going to maybe take that out to tens of thousands of light years away. Like, we will probably get to a point within a couple of decades where there is a supernova warning network that is for the entire Milky Way. And so if any supernova goes off in the Milky Way, we will get enough advance notice to be able to turn the telescopes and watch the thing explode. So then you'll get your video. And we will all see a supernova going off in the sky. Pitch wheel. Why do coronagraphs have a flower shape instead of being simple circles? So there's a few pieces of this puzzle that I need to get through. So if we want to be able to look at an Earth-sized world orbiting around a sun-like star, we have to block the light from the star. That's because the planet is like 1/10 billionth the brightness of the star. So we have to block the light from the star. That will reveal the planets nearby. And astronomers have many telescopes with coronagraphs equipped. Ones that are looking at the sun. They can block the surface of the sun so they can see the atmosphere around the sun. We saw this with the eclipse, where the moon blocked the light from the sun, and then we could see the faint objects. We could see the corona around the sun. We could see prominences on the edges of the sun. So that's what a coronagraph is doing. There's one in James Webb, there's one in the Very Large Telescope, and there's going to be one in the upcoming Nancy Grace Roman telescope, and there's going to be one in the Habitable Worlds Observatory. And each one is going to be more powerful. So the one that's going to be in the Roman Space Telescope is going to be able to sort of see objects that are about 1/100 millionth as bright as their star. So it'll be able to see, say, a Jupiter-sized object next to a regular star, and then the Habitable Worlds Observatory after that, that'll be the one with the coronagraph capable of resolving those Earth-sized worlds around sun-like stars. And right now, the way the coronagraph works, I mean, the main part is you just put this block in front of the sun, and then you're now seeing objects that are outside and around the sun. But the problem is that light is a wave, and light has a way of working its way back into your instruments. And so astronomers use a technique called interference, where they're able to take the light from various parts around the image, and they're able to interfere together and cancel it out, so that you're just left with whatever is remaining around the star, the planets. But the problem is that even that isn't powerful enough to get you that 10 billion difference in brightness. And so one of the ideas that's been proposed is called a sunshade. And this has got to be the thing that you're talking about. It's this flower petal looking sort of solar sail that would be floating out in space. And this would be a partner to a telescope like the Habitable Worlds Observatory. It would fly in formation at tens of thousands of kilometers away from the telescope, and it would be lined up perfectly. And then this sunshade would float directly in front of the star, and then the planets would be outside of it. But why the petals? Well, so once again, you still have the same problem, which is that if you have just a perfect circle that you're putting in front and you're lining it up perfectly in front of the star, then you're going to get this light that's going to come around the edges of the circle, and they're going to make it into the optics, and you're going to not be able to tell what is just blobs of light and what is the planets that are around the star. And so these petals are perfectly designed to create interference, to jumble up the light that is coming from the outside of the star. And it's not just like, just add some petals. Like, these have to be developed to like millimeter precision to be able to perform this effect. The distance between the sun shield and the telescope, as well as the actual shape of the shield itself, have to be perfect. And then you get that interference from the sunshade, you get the interference from the coronagraph that's on board the instrument, and hopefully all that's left are the planets that are orbiting around the star. And like James Webb is powerful enough that if there was no star there, it could see planets. It could see other Earths, things that are that level of brightness. It's just that the star is in the way. And so hopefully this technology or other technologies will work out to be able to block that light and get us to that 1/10 billionth where we can actually see other planets orbiting around other stars. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Jerry Orbrecht, CD, Buzz, RevMatch TV, Bexar, Conrad Holling, Mr. White, Michael Bond, David Falk, Drew, Staniforth Hopkins, and Duncan Hunt. Join the club at patreon.com/universetoday. Aaron Calhoun, how do astronomers determine the distances to galaxies? So astronomers have developed this pretty great distance ladder to figure out the distances to various things in the universe. So at the closest part, the first rung of the distance ladder is known as astrometry, or the parallax method. And the way you do this is, and like everyone who's watching this right now, do this together with me, okay? Put your arm out at, length, stick your thumb up, and then look at some background object, and then move your open and close one eye at a time. And what you should see is your thumb jumping back and forth, right? And so that is parallax. This is that you're looking at a object from two different perspectives, and then you can measure the geometry. You know how far apart your eyes are. You know how much your thumb is moving back and forth, and then, trigonometry, you can calculate the distance to your thumb. And so astronomers do the same thing at a much larger scale. They will look at some star against the background of the universe when the Earth is on one side of the sun, 150 million kilometers from the sun, and then they'll wait 6 months, and then we'll do the measurement again when the Earth is on the other side of the sun. And then they can measure that distance that this star is jumping back and forth between those two measurements. They know the distance that the Earth is traveling in that time. They know how the angle is changing from the two positions. And from there, they're able to calculate the distance to the star. And you can do this yourself. You can measure, say, really nearby stars, Barnard star, things like that. And you can actually calculate the distance to these stars. And so that process can go out to a pretty significant portion of the Milky Way. And the most famous telescope that's doing this right now is called Gaia. I just did an amazing interview about Gaia, which will be live probably within a couple of weeks. But that gets us those distances. But then astronomers have the next rung on the galaxy ladder, on the distance ladder, and that is Cepheid variables. There is a very specific kind of star that is nearing the end of its life, and it starts to go through these pulsations where it is sort of grows and then shrinks and then grows and then shrinks. And it's pretty dramatic. Like, it goes from a star that is, a little bigger than the sun, blasts out beyond the orbit of Mars, goes back in and just does this. And astronomers figure out that there is this measurement that you can make. There's this connection between the pulsations of the Cepheid variables and their intrinsic brightness, how bright they are. And so when you measure the change in brightness of one of these Cepheid variables, you can then calculate how bright this star is. When you calculate how bright the star is, you can know how far away it is. And so astronomers are able to then overlap the two things. They're able to overlap between the parallax method and the Cepheid variables. And that gets you out to galaxies. And in fact, when Edwin Hubble was measuring the speed of galaxies moving away from us in the universe, he was measuring the Cepheid variables, the redshift of the Cepheid variables in these other galaxies, watching them move away from us. And so now astronomers have a few techniques they can use to measure the distance to various galaxies, mainly Cepheid variables. They also use type 1a supernova, which are a kind of exploding star that goes off with a set amount of energy every time. And then from that, you can go all the way out to 3 4 billion light years away from us in all directions and measure the distance to the galaxies. And astronomers are always coming up with new ways to measure distance in the universe. They just keep adding them and overlapping them. And so there's, at this point, probably about 20 different methods of measuring distance in the universe, and they all just overlap with each other. And so you just figure out which one you want to use to figure out the distance. Kale Darkwind, who was your favorite interview? I don't like to pick favorites. But, I've had a lot of great interviews, ones that have been really mind-blowing. And sometimes you just feel it. Like you're just in such a vibe when you're doing the interview, talking to the person. They're well-spoken, deeply knowledgeable. Their audio is good. It really feels like just a great conversation. There's a bunch of people who I know are going to be really solid interviews that I can bring back on a regular basis. Paul Byrne, who talked about Venus with me, was great, but it's always going to be random. And I never really know whether or not the interview is going to work out or not. And I think, I do my best because I try to find people who have never been interviewed before, they've never talked to anybody beyond sitting around at the pub chatting with their friends over beer, right? And so I want people who aren't slick, who aren't really smooth, who are more interested in the work that they're doing, the science they're doing, than trying to promote themselves or try to promote something. They're motivated by the work, by the science, by the discoveries. And that's sort of the heart of the conversation. And it's always after the fact. It's always after when because I'm randomly picking people. I'm like, I see a paper come out. I see a piece of work that comes out and I'm like, oh, I'm curious. I want to know more about that. And so I reach out to the researcher. They agree to do an interview with me. And then we conduct the interview. And then sometimes it's great. Sometimes it's tough. And I have to sort of prompt them more often and come up with more questions to sort of keep the conversation going. And sometimes they have less than ideal audio, which is killed. There's a bunch of interviews you've never heard because the audio just wasn't quite good enough. And we were like, no, people are just going to complain about the audio. Even though it was an interesting interview, we just couldn't clean it up. I've learned that lesson now, where if I talk to somebody and I can tell their audio is really bad, I'll be like, okay, whoa, we can't do this right now. I'll send you a microphone. Get the microphone and then let's conduct the interview again. It's getting better now with everybody having higher quality microphones built into their computers, and phones are kind of amazing for doing these interviews. So anyway, I don't have a favorite interview. I'm always so in the moment. I'm always so interested about the person that I just talked with. So like the interview that I just did was with somebody about Gaia, and I got a chance to ask every single super nerdy, in-depth question about Gaia that has always bugged me. And I know plenty more about that telescope now than I did before I conducted the interview. And that's kind of the point. So my favorite interviews are the ones who are willing to answer all my questions to the level of depth that I need. Which I guess is the role that I play for you, right? I answer your questions and then I have to get these people on to answer my questions so that I can get the information to be able to answer your questions. Busy Billy B33. How do astronomers determine the age of a star? Figuring out the age of a star is actually pretty tricky because stars are giant blobs of incandescent gas. They are plasma, and so they are churning and roiling. And so when you measure the presence of various chemicals in the atmosphere of a star, the way you would do, say, carbon dating on Earth, you've got a piece of wood, you measure the amount of carbon-14 versus the amount of carbon-12, you measure the ratio, you know how long it takes carbon to decay, and that gives you the amount of time that this piece of wood was alive. Stars are trickier. And so for the longest time, it was really hard to know the age of a star to a very accurate amount. You could roughly tell that a star was part of, at a certain phase in the main sequence. So you could know the age of a star to within a few billion years. And you can get a hint at some of the chemicals that are in the atmosphere of the star. Various radioactive elements will decay into other elements. You can tell the presence of there. But like I said, because the stars are roiling and don't have a solid surface, it's really hard to make those kinds of measurements. The other thing that you can do is if the star is part of a cluster. And so generally the various stars in that cluster formed at the same time. And so the most massive stars have died as supernovae. And so you can tell how old the stars are in that cluster based on the mass of the largest stars that are left, the ones that didn't explode as supernova. But more recently, there's a new technique that's been developed that is much more accurate. It's called astroseismology. And this technique was developed on the sun. Astronomers were able to watch tiny wobbles on the surface of the sun, like earthquakes, but on the sun. And they were able to tell the interior of the sun. In fact, astronomers are able to use astroseismology to be able to see on the opposite side of the sun. They can see sunspots moving across the opposite side of the sun, and they know when they're going to appear on the side of the sun that we can see. And so this technique of astroseismology was adapted to look at other stars. And in fact, several telescopes have done this. TESS, which is mainly measuring the brightnesses of stars, looking for exoplanets passing in front of them, can also measure these slight changes in brightness that are coming from just these slight pulsations that are happening from the star. Most stars are variable stars, just they're not very variable. The sun is a variable star, but it just doesn't change very much in brightness. And so there is a connection between the variations that happen on the surface of a star and the age of the star. And so from this fairly new science, astronomers are able to start working out the ages of stars to a higher degree of accuracy. Jimdika, if we have roughly 5 billion years before the sun goes red giant, isn't it likely that we have the capability of altering the Earth's orbit in order to safely move farther out from the sun? We actually have a lot less than 5 billion years before there's going to be problems for life on Earth. We have about 500 million to 1 billion years. That's because the sun is increasing in temperature. And this increase in temperature is going to cause our planet to get hotter and hotter. And eventually the oceans will boil and the surface of the planet will be uninhabitable. And, at vastly longer scales than global warming. And so the solution to this is to move the Earth farther and farther away from the sun, which sounds tricky, and it is, but it's not, doesn't break the laws of physics to be able to do it. It just requires some very careful playing with gravity and geometry. And so what we need to do is we need to steal the momentum, the orbital velocity from some other object in the solar system, like Jupiter. And then we need to give that momentum to Earth. And if we did that, if we stole just a tiny, it'll never notice. Jupiter will be fine. It's not even going to change its orbit in the slightest. And yet we could start to steal that momentum for Earth, because Earth is dramatically less massive than Jupiter. It will have a larger effect on our planet, and we can start to spiral outward away from the sun in lockstep with the increase of luminosity that's coming from the sun. And so we can always keep the Earth at the exact perfect temperature and avoid that whole 500 million to 1 billion years, until the very end of the sun. We can just keep moving farther and farther away from the sun. So you're asking, how do we move the Earth away from the sun? How do we steal this momentum from Jupiter? And the way we do it is with an asteroid. We take an asteroid and we have it do a very close flyby of Jupiter, and then fly down into the inner solar system and make a very close flyby of Earth, enough that Earth is accelerated by the gravity, the mass of this asteroid as it's passing really close to the Earth. Essentially, the asteroid is doing a gravitational slingshot around the Earth, and it is giving us some of its momentum. And then the asteroid careens back out by Jupiter, does another pass of Jupiter, and then comes back into the inner solar system and just keeps handing off this little bit of momentum that's stolen from Jupiter. So in gravitational slingshots of Jupiter and Earth, back and forth. And eventually you just get this slight change to our orbit with each one of these interactions. And as long as you time it right and you don't hit Earth with your asteroid, or crash your asteroid into Jupiter, or you have to go get another one, then you can keep this pace going on and keep Earth the perfect temperature. And it's obviously like science fiction, but to change the orbit of an asteroid, I mean, we use DART and we smashed an asteroid and we changed the orbit of an asteroid. It was a very small asteroid, but you don't need a big asteroid to be able to do this. You just need to have the right asteroid come by the Earth the right times to slowly raise our orbit away from the sun. Alexis, why does the moon look bigger in the sky, even yellow at certain times? So the yellow part is because the moon's light is passing through the atmosphere of the Earth. And so when you think about the Earth is surrounded by this thick atmosphere. And when you look straight up, you're looking through the thinnest amount of the atmosphere. And when you're looking close to the horizon, you're looking through the most of the atmosphere that you can. And this is why generally, if you're using a telescope, you want to look straight up. You don't want to look at stuff near the horizon. You're looking through a lot more of the atmosphere, a lot of murk, and it's sort of bad for seeing. And so the wavelengths of light that are passing through the more of the atmosphere are shifted towards the red. The blue is scattered. The red is what you see. And so, that's why we get sunsets. Now, why does it look bigger, right? And I have definitely had this experience where you walk outside and the moon is really close to the horizon and it just looks gigantic. And then later on, the moon is much more overhead and it looks small and, it's normal size. I'm like, what's going on here? It's an optical illusion. It is your brain is messing up. The moon is exactly the same size as it always is. It is that your brain seems to think that the moon looks bigger when it's close to the horizon. And we don't exactly know why. It's something about the way our perception works with the brain, where if we've got a thing that we see, the moon, and it's close to things that we can see, like buildings or trees, and it feels like it's big, when it's just up in space, it looks smaller. And yet you can test this for yourself. Hold your arm out. Before we were holding out our thumb, this time, hold out your little finger, and you'll see that the moon is actually about the size of your pinky nail. And then when the moon is just rising and it looks big and gigantic and huge, just hold your arm out and then hold your finger next to the moon and you'll see that they are roughly the same size. And then a few hours later, some other night, when you happen to notice the moon high up in the sky, do it again. And you'll see that it is the same size. And there's great pictures where people have shown the moon rising from the horizon through all the way up to being high in the sky. And they just take an image every few minutes and then they just put all those images together and it's exactly the same size all the way up. It's all in our brain. It's so funny. But yeah, it's called the moon illusion. Brains are weird. All right, those are all the questions that we got this week. Thank everyone for joining, everyone who put their questions into the YouTube comments, and everybody who joined me for the live stream that I record every Monday at 5 p.m. Pacific time. So if you want to come, the show is twice as long and a lot of back and forth conversations. So if you want to join that, it's a really good time. We'll have a notification on the channel for when the next live show is going to be. Like I said at the beginning of the episode, not sure how this is going to work with my travel. So hopefully you will see a live event and hopefully it'll happen then. Now, I'm going to celebrate another small channel here, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Dennis Alberti, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mark Ansis, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Filer Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all our other patrons. All your support means the universe to us. So this week, I want to recommend you check out a channel from a good friend of mine, Ian Lauer. He used to work with Oceanside Photo and Telescope, is just an absolute monster at backyard astronomy, astrophotography. He knows what's the best gear to be able to look in the night sky. And he recently put out a fantastic video where he just explained soup to nuts, what's the best beginner setup to get into astronomy and to get into astrophotography. He gave, much better advice than I did. And he's great and one of my sort of favorite people. So I highly recommend his channel if you want just great telescope advice. Check out Ian Lauer's channel. All right, that's it for this week. We'll see you next week.